Hey guys, I wanted to film this as a video and I'm just going to have you watch this in class today so we can kind of move at our own pace with this and jump into practice problems as soon as we can. And as you're working on the practice problems, that's where you actually might need me a little bit more. So I have already written out the factual, informational part of the notes. So I'm going to move through this a little more quickly had I not done this already and I were writing them out. So as you need to slow down, just pause the video and write down the information. And then we will get to practice problems. So it is probably a page and a half of notes in your notebook. Okay, so this is about neutralization reactions, titration, and solution stoichiometry. And remember, I love the book, so if you need help or if you need some good visuals, then this is chapter 18, acids and bases, specifically pages 659 to 664. I have books in the classroom. You also have it on your single sign-on portal online. Okay, so we are doing a titration lab tomorrow, so we need to get some foundational things out of the way and also learn how to do calculations in order to do this lab. Okay, you're picking up the lab today, so you're going to need to get that pre-lab done tonight. So before we talk about the actual process of titration, you need to understand what a neutralization reaction is. This is simply a reaction, and you could kind of guess what this is anyway. Neutralization, trying to make a solution neutral. So you're just adding an acid and a base. Of course, they're in an aqueous solution, and they produce a salt and a water as they neutralize, as they mix together and combine. Water is in the liquid form, and by salt, of course, we mean an ionic compound, which is a compound between a cation and an anion. Always the cation first. Okay, this is a double replacement reaction. You've done these a gazillion times where you swap the partners. Okay, so it's going to produce water, and I do write water still as HOH because it is easier to balance. Okay, but of course the proper way to write it is H2O. Your cation comes from the base. Example, sodium hydroxide, right? Hydroxide is going to go to the water. Sodium is going to be the cation in the salt. The anion comes from the base. The hydrogen is going to join up with the hydroxide to make water, and the chlorine is going to join with that cation sodium to make the salt. So you might see some problems like this where it says write the neutralization reaction between magnesium hydroxide and hydrochloric acid. Okay, it doesn't give you the products, but you really don't even need to stress about predicting the products because you know it's just going to be HOH and then the other two cations and anions. Okay, be sure you're correctly writing the formulas. Magnesium hydroxide, you got to have 2 hydroxides to match with the magnesium 2+. Be sure you include their states of matter. They are aqueous. Acids and bases are going to be aqueous because they're dissolved in aqueous solutions. Everything happens dissolved in water. And they produce, every single time, water in the liquid form and salt, in a salt. In this case, it's magnesium from the base and chlorine from the acid. The cation from the base, the anion from the acid. Okay, and this is also usually aqueous. Go ahead and check your solubility chart, though, to be safe. Okay, you can also write the net ionic equation from this. This is the exact same thing we did last unit with solutions. Okay, your precipitate, or the one that does not dissociate, is going to be your water. Okay, the only things that dissociate are your aqueous compounds. Okay, so to write the net ionic equation, you split everybody up, magnesium plus. Guys, remember, I was not having you write the aqueous after those ions. If you are watching this and you have a different teacher, then stick with your expectations, which is writing the aqueous. I do expect you to write anything that's not aqueous. So that water, it's not dissociating. You better tell me why. It's because it's not aqueous. It's either a liquid, a gas, or a solid. Okay? And then your net ionic equation are just the ions involved in producing that non-aqueous compound. Okay. So moving on to titration, which is a process of, it is a neutralization reaction, and it's when you mix two solutions together and you don't know the concentration of one of them. Okay, so the end goal is to figure out this concentration of either the acid or the base. Okay, this is a big part of AP Chem. So get these definitions down. Okay, it is important. There are quite a few definitions in here. Well, not quite a few, a couple. Okay, titration is a process where an acid-base neutralization reaction is used to determine the concentration, and remember that's just molarity, of a solution. So you're going to react a known volume of a solution where we don't know its concentration. So we know we're going to have 500 milliliters or whatever of a solution, and you react that with a solution where you know its concentration and you know its volume. Okay, so there's a formula that allows us to calculate molarity and volume against another solution's molarity and volume. See if you can kind of predict that before we get there. So the process of this lab that we're going to do tomorrow, I do want you to write this down because it is, it's not a hard lab or a tricky lab, but it's a lot. So you need to have kind of an idea of it before you come in and just try to figure it out on your own. Okay, so the process is, in a flask, a known volume of a solution whose concentration we don't know is placed into the flask with an appropriate indicator. Okay, and we'll talk more about why you would pick one of these in a second, but your usual indicators are going to either be bromothymol blue or phenolphthalein. Okay, we did phenolphthalein in our indicator lab, and you saw that turns pink in a base, and I can tell you that bromothymol blue has a range of colors between blue and I believe yellow, and green is your neutral color. Okay, so then you're going to have a ring stand set up with a burette. We have not used these yet this year, so we'll talk more about the process of using a burette tomorrow. That is filled with your solution whose concentration we know. This is what we call the titrant, okay, or your standard solution. So in the flask is the solution who you don't know the concentration. In the burette is the solution that you know the concentration. And it can be an acid or a base in either one, okay? And you know the volume in both, right? Because you're controlling that. You're like, I'm going to put this much volume in here and this much volume in there. So then, tiny increments of a volume of the titrant, okay, so from the burette, are slowly and carefully added to the flask of the known solution, and you want to swirl that flask constantly, okay, until the reaction reaches what we call the equivalence point. You have to know that the equivalence point is when the moles of your hydrogen equal the moles of your hydroxide. Okay? You will know you've reached this equivalent point and your neutralization is complete when your indicator changes color permanently. So when it starts getting close to this equivalence point, your indicator is going to start slightly changing colors. Okay, if you were using phenolphthalein, you would see a tinge of pink, and then it will go away. Okay, so when you get to that point, you want to make your volumes that you're adding from the burette tinier and tinier. Okay, then when your indicator changes color permanently, it won't swirl away, and the fainter the color, the fainter the permanent color, the better. Okay, you don't want it to turn hot pink. You want it to be the slightest, faintest pink. Okay, now let's talk about when you would use which indicator. Okay, this color change, if I didn't say this already, guys, the color change, when you see that permanent color change, that's called your end point. Okay, equivalence point is the true stopping place. That's where your moles of your hydrogen equal the moles of your hydroxide. The end point is just simply your indicator telling you you're done. Of course, we want them to happen at the same time, but we do our best. The pH at the equivalence point is not always 7, okay? You think of a neutralization reaction as ending at the pH of 7, but that only actually happens if you are reacting a strong acid and a strong base. That only happens that if the strong acid and strong base will meet exactly in the middle at 7. If one is strong and one is weak, they're going to be off a little bit. So this is what we will be doing tomorrow, I believe. Don't hold me to it, but I believe tomorrow's lab we're going to choose a strong acid and a strong base. So the best indicator for that, their end point and their equivalent point, is hopefully at a pH of 7. So we're going to use bromothymol blue if we're going to do a strong acid and a strong base, because as soon as that solution turns green, then we know we're at a 7. The phenolphthalein is better if you're waiting for your pH to turn a little bit basic, because remember, phenolphthalein is a base, or I'm sorry, is pink in a base, and clear the rest of the time. Sorry, my computer logged out, and I'm hoping that this is still filming. So the last thing that we're going to do is a couple of titration calculations. Okay, write these down. These are some things that you already know. Remember, you can determine an unknown molarity using the dilution formula. M1V1 equals M2V2. Also remember that the units for molarity is simply moles per liter. Okay, that's literally the formula for molarity and its units. It is as simple as this dilution formula if your mole ratio for that neutralization reaction is 1 to 1. Okay? If it is not, then you need to do some stoichiometry because you need to take into account that those moles are not equal. Okay? Because remember, the equivalence point is moles of hydrogen equals moles of hydroxide. So this is just kind of like my little tip for you. If you have a 1 to 1 mole ratio, you're simply plugging into the dilution formula. If you are doing any any titration calculation and your mole ratio is not 1 to 1, then you have to use some stoich, which means you have to squeeze in your mole ratio. Okay, so this is kind of you kind of just have to play it by ear on this, but what I tend to do, and I don't want you to write mole of acid and base on this because sometimes you might be given the base and you're titrating the acid or vice versa. So I'm going to go back to M1V1 and V2 for this, but just know for titrations you technically should use MAVA, MBVB for acid and base. So if you are not using a 1 to 1 mole ratio, you still can think of your titration using this formula, but instead of the equal sign, you're just going to plug in a mole ratio, right? That's how you get your calculations to be equal, okay? And just a quick reminder, your volumes must be in liters, right? Because your units for molarity is moles per liter. So this worksheet is something that I think you picked up today. If not, then just pause this video and jot down numbers 1 and 2. And this video is getting pretty long already. It's 13 minutes. And so I am going to simply post the key to these two, and you give it your best shot using these two calculations, and you can look at the key online. I just don't want to go too long on the video and lose everybody. All right, work on numbers 1 and 2. This one's a 1 to 1 ratio. This one is not, once you write and balance those reactions, and get my help as soon as you need it.